developing a three-dimensional, three-body gravitational interaction simulation. Now, here it says three-dimensional, but for now, I'm just gonna start with how things would look like, how the interactions would look like, or how the equations of motions would be in a two-dimensional system first, in a two-dimensional environment first. So let's say we have a two-dimensional environment with the x-axis and the y-axis, and there are three coordinates which indicate the positions of the three bodies. So we have maybe a dot there, a dot here, and a dot here. These are where the three bodies are going to be located in, and they're just abstract points. This here is going to have a coordinate of p1, which is going to be x1 comma y1. This is going to be p2, x2 comma y2, and that here is going to be p3, x3 comma y3. Now, a useful thing to do for now, at this point, we're going to be indicating what the distances from each coordinate to each coordinate would be. So we're going to define something called r, the radius or the distance, from, I'd say, p1 to p2 as p1, p2, and we know that that's going to be equal to x1 minus x2 squared plus y1 minus y2 squared and square rooted. And this principle here is going to be same also for radius of the distance from p1 to p3 and the distance from p2 to p3. Alright, now we have our radiuses. What else is going to be useful? Well, they're going to need some masses. So let's say this object here has is going to have a mass of m1. This mass at point 2 is going to have a mass of p2, m2. And this here is going to have a mass of m3. Now, how do we show the interactions that go on between, I'd say, for now, mass 1 and the other objects? Well, there are two forces acting on m1, which is the gravitational pull so the force of gravitation between m1 and m2, and the force of gravitation between m1 and m3. So we're going to have this force here that goes like that, and another force that goes like this. But we know that there's the point of having two separate forces doesn't have any value. What we want to do is find what the net force is, and because the net force is what defines the motion of that object. And in order to get what the net force is, we're going to divide each of these forces into two perpendicular components that are parallel to these axes, because then we could easily add them and then get our net force at the end. Or maybe we don't even need what the net force is, because when we're going to make a simulation, we're going to interpret everything in terms of either one of the dimensions. So there's at the end of the theory, there's going to be a value for what the acceleration is, acceleration in the x direction, and the acceleration for the in the y direction. So we're going to have two values that define the motion of one object. Alright, so there's these two forces. How I'm going to label them is I'm going to say this force here is going to be F12 or F12, because it's basically the force from 1 to 2. And keep in mind that F12 would be different to F21. They're going to be in the opposite, they're going to have opposite, I hate the plus minus sign. So, okay, we're going to have this force here, F12. And we are also going to have F13, the force of 1 to 3. All right. now, as I said before, I'm going to divide these forces into two components. So this here is going to have components that go like that, perpendicular components, and this here is also going to have two components like that, 1, 2, 3, and 4. These four forces are basically I've divided one force into two dimensions, and we know that when we add these two up, they're going to be equivalent to this net force. And now, to define what these the magnitude of these individual forces are going to be, we're going to need to assign some angles. This here is going to be theta of 1, 3. Again, the angle from 1 to 3, and this here is going to be the angle from 1 to 2, theta 1, 2. Now, what do we know about theta 1, 3 and theta 1, 2 is that, first of all, we know that theta 1, 3, now let's look at theta 1, 2 first. When we look at theta 1, 2, that's going to be equal to, well, when we extend this triangle, we know that these two triangles, the big triangle that goes like that, and the small triangle that is about the forces are similar. And so the sine values or the cosine values taken from theta 1, 2 are going to be of the same value. And we know that this length here is x2 minus x1 or x1 minus x2. It doesn't really matter. But for now, let's just say it matters. It doesn't matter unless we always go in the same direction. So maybe later when I code, when I have to look at the force from P2 to P1, then it's going to be of the opposite direction. And so what we put as our x1 minus x2, x2 minus x1, for now it doesn't really matter. But for a sense of unity, I'm going to say it's going to be x2 minus x1 here. So the target, I say, the target object, the coordinate of the target object minus the coordinate of the, I'd say, the influenced object. That's going to be what our values for x2 and x1 is going to be. So the length here is going to be x2 minus x1. And here we could say that this here is equal to, again, y2 minus y1. Alright, so we know that theta 1, 2, then, well, let's say cosine of theta 1, 2 is going to be equal to r, as we define here, so r p1, p2, and our numerator is going to be, because it's cosine x2 minus x1. And you're going to see why I chose cosine, not sine. But for this triangle here, I'm going to pick the sine function for now. So we know that sine of theta 1 and 3 is going to be equal to r of p1, p3, from p1 to p3. And our numerator is going to be, it's the sine, so it's going to be x3 minus x1. Again, target minus our moving object, our moving object. So we have these two cosine and sine values. And the reason I did this is because first of all, I'm going to look at the forces in the x direction. And so the force, the x component of this force is going to be F12 times cosine of theta 1, 2, because it's the adjacent side we're talking about here. So we could say that, well, if the x component of the force of the force acting on object 1, which I'm going to say is F1 of x, that's going to be equal to F12 times cosine of theta 1, 2. So F1, 2 times cosine of theta 1, 2. And here it's going to be different. It's going to be F1, 3 times sine, because it's the opposite side now that we are talking about. So F1, 3 times sine of theta 1, 3. All right, so far so good, but we still don't know what the values for our forces that we're going to have to put in these two values are. We have an expression for cosine and sine, but we don't have an expression for F12 and F13. But we could know that by Newton's law of gravitation that says the force is equal to gravity. Wait, not gravity. The gravitational constant, the universal gravitational constant times m target, m moving object. No, m. I'd say m the mass of the first object times the mass of the second object over r squared. And so let's say you could say that F12, F12 is going to be, well, we have g times mass of 1 and mass of 2 over radius, again, P1, P2 squared. And we also know that F of 1, 3 is going to be similar, but it's going to be m1 times now m3 over radius of P1 to P3 squared. All right, we now have all of these. Now let's compute what f1 of x is going to be. We have f1 of x, and I guess I won't need the magnitude sign because we all know that this force is only in the x direction. It's the net force in the x direction. The net force in the x direction. And so we get here F12 times cosine theta 12. And so we have that here times this here. And we can see that when we multiply the denominator, we're going to get the r of P1, P3 cubed because we have a squared here and a power to the 1 here. So we have radius, the distance from P1 to P2, cubed over, when we multiply the numerators, that's going to be g times m1, m2 times x2 minus x1. And we could say then, we could also say that, and so this is our first term, and now for the second term we have f13, which is going to be that times sine of theta 13, so that, and again we have the cubed of the radius in the denominator, but it's P1 to P3, so we have r P1 to P3 cubed in the denominator, and our numerator again is going to be g times m1 m3 here times x3 minus x1. And so basically, but one thing that I want to do here is get the minus g over r P1, no, the minus g out, because then we're going to have x1 minus x2, which is a I'd say a sequence of terms that I prefer because everything here we have P1, P2, M1, M2, and so let's just say we have x1 and x2 in that same order. So we're going to have the force that object 1 experiences in the x direction, that's going to be equal to minus g times P1, P2 cubed over m1, m2, x1 minus x2. Again, we're going to have, or we could have a bracket and say minus g, and here we're going to have a plus m1, m3 of x1 minus x3. We notice that these two, the direction is changed, the sequence of the subtraction is changed, and we're going to have r of P1, P3 cubed. So that's going to be our value for the force in the x direction. But we said, well, yeah, we know the force, but now we have to know what the acceleration is in order to make our simulation. Basically, acceleration is all we need, because we could say that, position of x in the x direction of whatever object, first object, second object, third object. I'm just going to put that as n. Well, Pn, the position of my nth object, is going to be that's going to be, well, let's say, well, this is basically Euler approximation, but we're going to have let's say P1, my first object, and its x coordinate and the n plus 1's value of that is going to be equal to p1 of x, n's value plus the velocity, the n's value. And then someone says, oh, and what's the n's value of the velocity? Then I could say that, oh, the n plus 1's value of the velocity, we could define that as vxn plus acceleration. So we need this term here to compute our change in velocity and then our change in position as well. Alright, so we know that well, net force is equal to mass times acceleration. And so acceleration is basically our net force divided by the mass. And we have our, well, we don't have our net force, but we have our net force only in the x direction. So we could get our acceleration in the x direction from this equation. So we have our acceleration of object 1 in the x direction is basically going to be this entire expression divided by our mass of 1, our mass, which is m1. And so we have minus g divided by m1. But we could also do that not here, but we could basically, cancel out the m1 from both terms. And so we have minus g times, we have our m1 canceled, so we have m2 x1 minus x2 radius cubed plus, again, radius cubed over m3 times x1 minus x3. And that's going to be our value for the acceleration in the x direction of our object. Alright, that's a1 of x done, but still we need a lot more to do. We need a1 in the y direction, we need a2 in the x direction, we need a2 in the y direction, we need a3 in the x direction, and a3 in the y direction. And not only that, we need our z quantities too. So we need our a1z, we need our a2z, we need our a3z. So in what time are we going to do all of that in that same process? Well, we don't have to do that. Because you see, well, let's look at a1y first. Let's erase what we don't need. So let's erase everything else except for our diagram. Yeah. Okay, let's look at a1y. What would a1y be? Well, we do the same thing. We have our forces, but now we don't multiply f of 1, 3 times the sine. Now what we're going to do is multiply this here. No, not that. So we're going to multiply this, the force here, times the cosine, because now what we're dealing with is not this force here, but this force that goes vertical. And the same thing for here. We're not going to deal with the force in this direction, but we're going to deal with the force in this direction. So for here, we're going to use the cosine function, and for here, we're going to use the sine function, which is very different to what we did here, which here we used the cosine function for this force, and we used the sine for f13 and the cosine for f12. So we're going to reverse things a little bit. But we see that the effect of that doesn't really change our expression greatly, because when we deal with, so let's say we're getting our value for this force here. Well, then that's going to be f12 times sine of theta 12, and we know that sine of theta 12 is going to be y2 minus y1, or minus of y1 minus y2. And that's going to be the same for here. We're just going to have the y values subtracted from each other, not the x values. So everything else then is going to be same. We're going to have sine of, everything else is going to be same. And so we could say that a1y is going to be minus g times everything else same. We have our denominator same, which is the radius. And we're going to have minus 2 again, m2 again. But now what we're going to have is not x1 minus x2, but we're going to have y1 minus y2. And here again, we're going to have m3 of y1 minus now y3 over the same thing. So we have our a1x, a1y, and you get the point. Let's say we're going to have to find, well, what's going to be, let's say a2 of x. Well, then a2 of x is going to be same. Just going to be that our radius is going to be not p1, p2, and p1, p3. It's going to be p2, p1, which is basically p1, p2. But the second term here, the radius is going to be p2, p3. And here it's not going to be m2 and m3. It's going to be m1 and m3 because m2 is our target now. And for here, it's going to be not x1 minus x2, but it's going to be x2 minus x1 first, because now x2 is our target object. And for here, it's going to be again m3, because m3 times not x1 minus x3, but x2 minus x3. And you get the point. Everything else we could do in the same way. And okay, so let's say we have a value for that, we have a value for that. So here done, that done, that done, x and y is all done. Well, then what's the value for a1z, a2z, and a3z? Well, we know that that is also going to be in the same form, but just that it's going to be z1 minus z2, z1 minus z3, or whatever, z2 minus z1, z2 minus z3, or and so on. And how do I know that? Well, okay, so how do I know that? Let's say we have this coordinate, we had this 2D plane, but now let's imagine here, everything here as a 3D environment. So we have our z coordinate, but it's just that our z coordinates now here are all 0, and that's why we made these expressions. But you saw that the expression for a1 of x does not involve anything related to the y coordinates. Just maybe yeah, we did use the y coordinates in calculating our values for the distances, but except for that, a1 of x has nothing to do with the y coordinate, and the same logic. A1 of y has nothing to do with the x coordinates. We don't have an expression for x here, just in the distances, but that's of course. And so we could say, well then, if I say that we're looking at this not in the xy Cartesian plane, well, let's say everything here was in the x and z plane. Well, then we could basically do the same math, and we would notice that everything in terms of y, so all of these are going to be substituted by z1, z2, and z3. And so that proves the fact that, well, a1z then is going to be equal to minus g times the same thing, but only the only change would be that we're going to have z1 minus z2 plus m3 of z1 minus z3 over r p1 p3. That's going to be the same. And another change that I mentioned was that, well, for example, when we're going to have to calculate r of p1 p2, let's say, then that's not going to be x1 minus x2 squared plus y1 minus y2 squared, but there's going to be an additional term inside the square root. That's going to be x1, z1 minus z2 squared, because we're dealing with distances in 3 dimensions. So we're going to have to Pythagoras that, and then Pythagoras that inside. And so we're going to have that squared, that squared, that squared, which is going to look like that. That's our p1, p2, and the same thing for p1, p3 is going to be, x1, x3 squared, y1, y3 squared, z1, z3 squared. Same 2, 3 is going to be 2, 3 squared, 2, 3 squared, 2, 3 squared. You get the point. All right, so that's the theory done. So with all this theory, hopefully we could be able to make the three-dimensional three-body gravitation simulation. And one thing to point out before I go on to coding is that the tool here that I'm going to use is going to be processing. I'm going to use the tool processing for this time simulation. And the thing about processing is that it only deals with two-dimensional cartoons, or two-dimensional, let's say, sketches, two-dimensional drawings. And so we're going to have to implement the sense that it's a three-dimensional simulation in a two-dimensional viewpoint. So what I'm going to do is, let's say we have our three-dimensional three-dimensional plane, and let's say we are going to have to plot some point that has the coordinates x, y, and z. Well, how am I going to do this? Well, the trick here is that when we look at the z-axis, we see that it moves in this axis over here. So it's the same thing as when we're drawing our three-dimensional axis. You know that the board here is not actually a three-dimensional object. It's just a two-dimensional, it's just a board that we somehow managed to make the idea that it is a three-dimensional space by having an axis that is I'd say 45 degrees from each axis. And so it gives the sense that it's a three-dimensional plane. So I'm going to do the same thing in my processing environment. I'm going to say, well, to plot this in a two-dimensional space, I'm going to say that's going to be equal to x, of course, and then y. But we see that, well, when we move, let's say we have to move something 3 to the x direction, 2 to the y direction, and say 4 in the z direction. Well, then what I'm gonna do is, well, move this 1, 2, 3 in the x direction, move it 1, 2 in the y direction. But now in the z direction, I'm gonna go the same 1, 1, 1, 1, the same magnitude, but I'm gonna do that 4 times. So that, and then that. So our point will actually be located here. And that here, we know that the length of this is 4. And so we know that we have went 4 minus root 2, minus 4 over root 2 in the z direction. And again, minus 4 over root 2 in the y direction. And so we're going to have, when we're going to have to plot x, y, z, generalized, we could say that it's going to be plotted in a space that's going to be x minus z over root 2, here, root 2 minus 4 over root 2, comma y minus z over root 2. That's going to be how I'm going to plot a three-dimensional coordinate in a two-dimensional Cartesian space. But still, for example, we have this point here. The coordinate of this point is 3, 2, 4, but still it could be anything. It could be a dot that's plotted in the xz plane. It could be 0, 0 times minus 2 or something. So we don't know where exactly this point is, because there is an infinitely many number of points that could be. So I'm going to depict that in terms of the size of the object. So the larger my z value is, that's going to look larger, and the smaller it is, so somewhere over here, it's going to be, when this is like minus 4, it's going to be like a dot like that. So that's how I am going to give the sense that my simulation here is not two-dimensional, but actually a three-dimensional simulation. And so yeah, that's the theory. That's the end of the theory. I hope you enjoyed it, and yeah, see you in the next video where I'm gonna talk about, where I'm gonna actually code the three-body, three-dimensional gravitational interaction simulation. Thank you so much.